What is nanotechnology? Nanotechnology is the science and engineering of small things, in particular things that are less than 100 nanometers in size. Nano is an C prefix and comes from the Greek word for dwarf, nanos. 1 nanometer is 10-9 meters, or about 3 atoms long. At first, it can be hard to comprehend the nanoscale because it is so much smaller than our everyday experience. While we know intuitively that a dime is smaller than a basketball, and even that a red blood cell is smaller than a marble, we have no experience with objects that are billionths of a meter in length. When was the last time you put your hands around a strand of DNA or measured the diameter of a flu virus? Here are a few comparisons to help understand how small a nanometer is. An average human hair is about 60,000-100,000 nanometers wide. Your fingernail grows a nanometer every second. A sheet of paper is about 100,000 nanometers thick. In 1 inch there are 25,400,000 nanometers. To explore the size of the nanoscale in relation to other scales, there are some great interactive sites such as Scale of the Universe, Powers of 10, and Nanosize Me. Nanotechnology is often divided into 2 parts. Nanoscience, where researchers learn about the chemical and physical properties of materials at the nanoscale. Materials at 1-100 nm are called nanostructures. They are the smallest things that can be made. Nanotechnology, where researchers develop and apply materials at this scale to develop new products or methods. That is, turning nanostructures into usable tools and applications. Why is the nanoscale of such great interest? Scientists have discovered that materials at such small dimensions can have significantly different properties than the same materials at larger scale. Here are some examples. Gold at the nanoscale interacts differently with light, resulting in colors that differ greatly from the lustrous golden color of the bulk material. Medieval stained glass makers did not know they were working with nanoscale materials when they used these properties to create their masterpieces. Bulk aluminum is the stable material we use for soft drink cans, bike frames, car parts, etc., but at the nanoscale it is explosive. Copper at the nanoscale is transparent. These unique properties provide us with endless possibilities for improved devices, structures, and materials if we can understand these differences and learn how to control the assembly of small structures. There are many different views of precisely what is included in nanotechnology. In general, however, most agree that 3 things are important. The materials must have a small size, measured in 100 seconds of nanometers or less, in 1 dimension. The materials, or products made from them, must possess unique properties because of the small size. Scientists and engineers must be able to control and manipulate the structure and composition on the nanometer scale in order to control the properties. Nanostructures, objects with nanometer scale features, are not new, nor were they first created by man. Nature has many examples of nanostructures such as hydrophobic leaves, iridescent butterfly wings, and a gecko's foot. Through biomimicry, scientists and engineers are creating new products using these nano-inspired features. Similarly, there are many natural nanoscale materials such as catalysts, porous materials, certain minerals, and soot particles, for example, that have unique properties particularly because of the nanoscale features. What is new about nanotechnology is that we are now understanding and controlling some of these structures and properties to make new materials and devices. We have entered the era of engineered nanomaterials and devices with many commercial products already available. The other fundamentally different area of nanofabrication results from starting at the atomic scale and building up materials and structures, atom by atom. It is essentially molecular engineering, often called molecular or chemical nanotechnology. Here, the forces of nature are used to assemble nanostructures from the bottom up and is called self-assembly. There are many exciting applications that combine both bottom-up and top-down processing to create, for example, single-molecule transistors that have large leads fabricated by top-down, and single-molecule assembled from bottom-up. One area of nanotechnology has been evolving for more than 40 years and is the source of the great microelectronics revolution, the techniques of micro and nanolithography and etching. This is often described as top-down fabrication. Here, small features are made by starting with larger materials and patterning and carving down to make nanoscale structure and precise patterns. Complex structures including microprocessors containing 100 seconds of millions of precisely positioned nanostructures can be fabricated. Of all forms of nanotechnology, this is the best established. Production machines for these techniques can cost millions of dollars, and a full-scale microprocessor factory can cost more than $1 billion. In recent years, the same top-down nanoprocessing techniques have enabled many non-electronic applications, including micromechanical, microoptical, and microfluidic devices. Nanotechnology combines physics, chemistry, biology, engineering, biochemistry, biophysics, earth and environmental science, and materials science. It is a highly interdisciplinary area, meaning that it involves ideas integrated from many traditional disciplines. Some universities have begun to issue degrees in nanotechnology. Others view it as a portion of existing academic areas. Either way, there are many career options open to trained scientists, engineers, and technicians, and the demand for these skilled workers continues to grow. The federal government believes that nanotechnology is one of the most important research endeavors for our country. In 2001, it established the National Nanotechnology Initiative as an umbrella organization to promote and organize nanotechnology research across the government. Under NI, 20 federal department and agency units undertake nanotechnology-related research with a current budget of approximately $1.4 billion per year. An aggressive set of technology milestones and grant challenges have been established by NI. In 2004, President Bush signed into law the 21st Century Nanotechnology Research and Development Act, which further promoted nanotechnology research. Other countries around the world have followed with significant programs in nanoscale science and engineering.